And hello, everybody, and welcome back. I'm glad you're here, and welcome. And we'll look around. We are continuing our discussion of the strength of the human mimicking robot hand. Strength is not that hard to get if the hand is not too small, but things get complicated if you also want the hand to be as small as a human hand. This distance for this hand right here is 4.5 inches, and this distance is 4.75 inches. So it's a small hand. Let me rephrase that. It's a small hand for a robot hand. It's the same size hand as a human hand. This distance is about 2 inches. And it's fun to start out with the collection of hands. Now, so let's see, we'll go back over here. We started at the tip of the finger and worked our way back. We're getting ready to start talking about the micro hydraulic cylinders that act as the intrinsic muscles of the hand. But I thought before we get into that, we might want to talk about this frame, because the frame acts as the foundation that allows the hydraulic cylinders to do what they're doing in terms of controlling the hand. And it also, as part of a strength discussion, remember, and this is the hand grasping onto a metal rod, this hand is going to be able to hold up 200 pounds. And so it has to have a frame to connect to that's strong enough to allow it. And that is this frame. I took it out to show it. And I'm also showing the pinch format of the robot mimicking hand. And we can use the magic of computer digital work to have the equivalent of removing everything other than just the hand. And that allows me to show the opposable thumb and the pinch type activity. You'll notice that this finger is AB, abducted away from the midline a little bit. That's really how human beings grab onto things. And the thumb is also just faintly abducted, and that's what allows the index finger, to be brought down against the thumb. And of course, let's see what is going on. We can take a peek here. This is in Bing, the Fiskard Lighthouse in Esquimalt Harbor. 2 windows. I tell you, that looks awfully small. When the big waves are coming this way, you have to talk to me for a while to want to live here. But there it is, the Esquimalt Harbor Lighthouse. And we have some other things that we'll talk about. And of course, we always want to bring this in. Hello and welcome again. I do have a YouTube channel. I try to send these videos to my YouTube channel. I have a web page. Here's my website, Piston Robot. Here's the web page. Give the robot a hand. I try to put all the YouTubes on that web page. Always anything that's real, but particularly stuff where you have hydraulic cylinders and pressure. Any physically real object could potentially hurt somebody. If you are managing a physically real object, you should manage it. My advice, you should manage it in a manner that is legally allowed and reasonable and safe. My advice is, if you cannot manage it in that way, my suggestion is do not create it as a physically real device. And I've already talked about this is sort of my Turing test for a human mimicking robot hand, and we're talking about strength. And I did let the mannequins help me. I know people will say this hand is not possible, but I think it is possible, and I just want to very meticulously, part by part, show that it has the strength to do what we want it to do. All right, and so here we go. We're talking about the frame that supports the hydraulic cylinders that allow the finger to move, and in addition they support the metacarpal phalangeal joint. And I can't go really slow in a 15-minute video, but this frame can be split out. And remember, the yield strength of the 2205 alloy stainless steel is 65,000 pounds per square inch. So we can look at all these parts. These metacarpal phalangeal joint cardanic articulations are bolted to this piece of metal, but what really provides strength for an individual finger is this strip of metal right here, and that has a size of 0.02 square inches. So it has 1,300 pounds of tensile strength and about 650 pounds of bending strength and compressive strength and shear strength. And this is just 50 pounds. That's all the finger is putting on it, is 50 pounds. This bar across the top adds rigidity to this. This bar is 0.06 square inches. So this bar can take 2,300 pounds of tensile strength and almost 1,100 pounds of bending strength. These channel irons, are these square tube sections, add rigidity. There's a plate in the front that holds the metacarpal phalangeal joint, and there's a plate in the back that holds the hydraulic cylinders that allow abduction, adduction, and flexion extension at the level of the intrinsic muscles of the robot hand. And this has a surface area of 0.07, so 4,500 pounds of tensile strength, 2,200 pounds of bending strength and shear strength, and this is the same type of number here. And finally, in the back here is this plate, and this plate is what the abduction, adduction hydraulic cylinders are against, and that plate has 10,000 pounds of tensile strength and 5,000 pounds of bending strength and shear strength. So that's the strength of this frame. Oh, and all of these bolts are hex head 1.4 millimeter M1.4 2205 alloy stainless steel bolts. Each one of these bolts has a tensile strength of 156 pounds and a shear strength of 75 pounds. And I think what I'm demonstrating here is that this frame has all the strength you could want to support these fingers. And there's one remaining thing to look at, which is the big strength issue, which is when this finger is wrapped around a metal rod and this whole entire hand is holding up 200 pounds. And the frame is easily strong enough for that. The question is this place here where the metacarpal phalangeal articulation joins to the frame, how is that going to work? So that's the next thing we're going to talk about. And the conversation gets really quick here. This is the hand pulling down, but that's no different than if this bar was pushing up. It's pushing up with 50 pounds of force. Here is the ligament that curled up the finger. So the pulling down point is right here where this ligament is. And you can see that this bar is not above this point. The bar is moved out by 17 millimeters, and the anchor point is over here at 25 millimeters. And the torque is, if you did millimeter pounds, it'd be 17 millimeters times 50 pounds. And the torque so that's a torque that makes this want to go that way. So you have to put a torque over here based on this bolt that makes this want to go that way. And so that means you have to push up on this. But since this is 17 and that's 25, you don't need 50 pounds over here. You need 50 times 17 divided by 25, which is 34 pounds. So this has to push up with 34 pounds in order to keep this finger horizontal. And this is very easy to understand if the bar was directly above the pulling point, but it's not. But it doesn't matter, it's 34 pounds. And the question we have to answer is, what will happen if this is pushing down on this plate with 34 pounds of force? All right, and so here we go. I got to go fast. This is the piece of metal that it's pressing on, this metacarpal phalangeal joint. And we can measure in feet how long this piece of metal is, 0.13540 feet, and how wide it is, 0.003615 feet, and we can measure the thickness of it, 0.00395 feet. And that's all available to be measured. And we can also measure where this metacarpal phalangeal joint support structure is. So it starts at 0.03014 feet and it ends at 0.06606 feet. And those are all measurements we can do in SketchUp. And we have this ClearCalc calculator. It does require that we obtain the second moment of an area, and that's done with a rectangle, and that's at width 0.036 feet by 0.0039 feet. And that gives us over here the L, or the second moment of inertia in inches to the fourth. The beam is 0.13 feet long. The Young's modulus of the 2205 alloy stainless steel is 27.6 million pounds per square inch. The cross-sectional area of that area is 0.02 inches, and the second moment is that. The beam is this long, it's fixed. We have this distributed load. Now the distributed load is in pounds per foot. So we have 34 pounds of force being pushed against a very small amount of feet, and it comes out to 946 pounds per foot. And the location of this is between 0.03 feet and 0.06 feet. And what it shows us is the shear is 25 pounds, which is easily withstood by that metal. And the deviation of the metal is 0.005, so 5/1000ths of an inch, which means that 34 pounds of push is easily withstood by that piece of metal. And the summary of this is this ligament is pulling. I didn't calculate this ligament. It's actually 50 plus 30. So it's pulling down with 84 pounds. This is pushing up with 50 pounds. This is pushing up with 34 pounds. And this is all immobilized and stabilized. And in order for that to do that, this metacarpal phalangeal joint is pushing down on this plate with 34 pounds of force, and that plate, when it does that, will bend by 0.005 of an inch. And she is pushing on her fingers and pointing them right at me, saying, look, you're done. So I'm going to stop talking, and we'll do another video in a little while.